So today we go to the IMU part, and the IMU is the most tricky sensor because if you recall, for the last few days we've been using observations that couple with pulse only, right? Camera, LiDAR, ultra wideband ranging measurement, the observation only coupled with the pulse. But this boy over here, it's getting into the derivative domain. So that's why it's tricky. And then I will show you some research on it later. But so just to get the terminology. So when we talk about IMU, you, at least in the literature, people mean the 6 degree of freedom IMU, which covers accelerometer and gyroscope, right? One chip, two devices, two types of measurements. And what they measure is the angular velocity and acceleration, but in the body frame. This is very important because some people can naively think they can integrate and get you some position, but that's in the body frame. It's not straightforward. So when you buy an MU, some people can put in another magnetometer, and by the virtue of having 3 pieces of hardware, they call it this 90 degree of freedom MU. Then sometimes people put in some algorithm in the embedded system, and they call it the heading reference system. So the terminology is like this. So IMU, how many degrees of freedom? 6, yeah. So the standard, like when we talk about IMU, is supposed to be like that. Because magnetometer is not reliable. It can give you absolute heading, but it's not reliable because you can be interfered by all sorts of electromagnetic interference. Okay, so now we get to the derivative domain. In physics, we define the angular velocity in the Wolfram. So if you have a rock flying in the air, right? This rock is a rigid body object. It has its own orientation. So the Wolfram is this one. Right? So it has its own angular velocity, and it has its acceleration in this body frame. But the IMU measures things in the body frame. So we have this relationship. This is dynamical relationship. The derivative of the orientation is the angular velocity crossed with the orientation. And equivalently, we can flip this one to this side by changing from the frame. Okay? This is just identity, so you don't. There can be some lectures to explain how they derive this, but it's not important here. If you write in quaternion, it's in this form. Okay? So, straightforward. The position, the derivative of position is velocity, the derivative of velocity is the acceleration. So, this is the physics. In terms of engineering, the IMU measures the IMU measure, let's just ignore the noise and the bias here. The IMU measures the angular velocity and acceleration in the body frame. We can write out the physics. So angular velocity in the body frame is angular velocity in the work frame multiplied by the orientation, inverse. Okay? Okay. This rotation matrix is converting the coordinate in the body frame to the work frame, but now we're going from the work frame to the body frame, so it's inverse.
Which is the inverse?
So R here is implicitly converting a coordinate from the body frame to the work frame. This one is in the work frame, right? So you have to inverse this one to convert it to the body frame.
I just think T is a very confusing notation for inverse.
Oh yeah,
because it's rotation.
it's a orthogonal, so it's easy to -1. Yes. So
But
it's okay.
it's same
This is it.
for rotation matrix. It's same.
Yeah. So the IMU measurement is corrupted by the noise. First the noise. So it's the noise. And the noise are Gaussian. So straightforward. They also have the bias. the bias is some kind of mechanical defects in the design, something. So if you, for example, if you put the gyroscope at rest, right, you assume you're supposed to get 0. Or you can get some noisy measurement. So this is omega, and then this is t, and then if you sample the data, you can get something like this. If you average it, you're supposed to get 0, but you don't get 0. You get something like z, usually 3 to the power of 10 minus 3, something like that. So you can still have bias. Accelerometer the same. So it's some kind of defects in the, it's some kind of like engineering defects. And the biases, they model the biases by the random walk process, meaning that the derivative of this, it's supposed to be a constant, but it drifts somehow, so they model the drift in a stochastic manner using the Gaussian process. Okay. Any question now? Now this is important. Any question?
How do they do the random walk thing?
How do they do? The random walk is a model.
In the Gaussian process?
Yes. So the model. So they probably, I guess, some engineers would just lock that, just put the RMU there for like days. And for example, every 1 second, 10 seconds, they're going to take the average and they're going to see what the average changes over the day. So this is a very standard model in literature when they talk about the RMU measurement. RMU measurement measures the angular velocity and acceleration in the world frame, in the body frame, corrupted by noise and bias.
So eta is Gaussian noise.
And,
Yes. Yeah. So then it's a Wiener process, no?
Wiener process, you mean the random walk, right?
Yeah.
The random walk is for
This
bias. Yeah.
How does the B dot equals eta come? Is it just how it's defined?
Yeah.
If you, well, what do you mean? This is,
B dot equals eta. Why?
this is a model. It's a model.
This is the random walk.
It's a random walk model. So it's like,
So maybe it's easier to think of it as you say b dot equals 0, that's my model, then it will be the same, plus noise. The noise is the one that drives the change, but there's no way to model that change. The only thing you can say, there's some random change.
right? It's a, let's say bias is supposed to be a constant, but it's corrupted by some noise. Right? This is a constant, but it's also corrupted by some noise and it changes all the time. No, sorry. Should be 0 here. Should be 0 here.
And why is it B dot? Why not B? When
B dot
Change
is
in
the
B, so how B, the bias, develops over time is by changing with the Gaussian noise at each time step.
right?
So it's additive.
So if you measure the RMU over time, ideally the bias, because you leave it at rest, so there's no influence, so you are supposed to see this kind of pattern, this kind of noise, right? But it's not, it's like this. So there's a bias there. Right? But if you put it in like maybe 1 day, it's like this. But if you put it in 2 days, it's going to have some change. So that's why they model that process using this one. And this one is actually quite small. This one is actually quite small. It's like if you have the this one, the covariance of, for example, omega is about to the 1 to the power of 3. But the sigma of the bias for this one is to the power of 6. So the change is very small. Okay. So we are clear about what the RMU measures, right? Now this is supposed to be in the quiz. You want to get it answered now, or you want to think about it for a while?
Which one?
So this is win. It's a legitimate Vietnamese stamp. Like we have the Beckham of Vietnam, but we have a very famous footballer. His name is Min, and he builds a visual inertial system for a living, and he chooses. So he chooses the IMU frame to be the body frame instead of a camera, right? So why should we be like him?
Because
Let's see. You have an idea?
The orientation.
She
No,
was
that-
suffering with the IMU from the OBLAM. So
Yeah, yeah, I suffered 1 day.
You can model
It's also my
orientation as
question.
well.
it's mathematically impossible to. I mean, even if you have noiseless, no bias, it's mathematically impossible to recover the motion from the motion of a camera from the IMU measurements. Can I should I repeat? Even if you have a perfect IMU with a noise and bias, it's mathematically impossible to recover the camera motion from the IMU measurements.
That's because it's separated or what?
That's
So
because of the
it's
separation.
Yes,
And the separation,
it's fixed. So you know.
so you want me to write it down? You want to wait until the quiz?
But so you, I guess, I don't know. So you model things around the IMU in its body frame, and then you have a rigid body transformation to the camera.
Yeah, you would think transformation would be enough, but no,
No.
mathematically you still need something else,
Okay.
an extra spice in that. I want to show it. It's actually.
is it the inertial matrix?
Let me show you how. So, how do I turn off this?
Press B. If you press B in PowerPoint, your screen becomes black.
B.
It's supposed to be. Oh, now it's maybe something else.
No, it was black for a while.
Even
You have
if
to
you.
hold the button.
Okay.
Blue is fine.
That's fine, that's fine. Even if you have perfect, even if you have perfect integrator, you still cannot get the motion back. So if I have a camera frame, right? X camera, Y camera, Z camera, and then this is the MU. Next. Which side Y
You
should
go
go?
into the whiteboard.
Out from the
Yeah.
No, into. Yes, yeah.
This should be this one.
Oh, Z. Yeah.
MU. Let's just say. Okay, let's just say the orientation is.
Well, left-handed system.
Whatever, it's not important.
It was fine, it was fine.
No,
No, I
no.
don't
Let's just
think-
say the orientation is the same. Because you can actually put the IMU in whatever orientation you like. Right? So, let's just say you have an IMU in the same rotation, same orientation with the body frame. So position of the IMU is the position of the camera. No. So let's just say the position of IMU in the work frame is the position of the camera in the work frame plus the rotation of the camera in the work frame multiplied by the translation from the camera to the body
Camera to idea.
to the camera. This one should be C, this one should be I. Right? This one is the translation of the IMU in the camera frame. Take a dot. You take the dot. You get the velocity of the IMU in the work frame equal to the velocity of the camera in the work frame plus R omega C T plus right? And then you take another dot. This is a dot here, right? what you have is acceleration of the IMU in the work frame. This acceleration of the camera frame in the work frame equal to R. I probably require plus R. So you see the problem now?
No.
Sorry.
This one is the angular velocity. You can measure from the MU or from the sensor. This one is acceleration. You can measure from the sensor. This one is angular acceleration, which we don't have any sensor to measure. Right. So you see, we don't have enough sensor data to recover the motion. Get it? Get it? Because, get it? Which part you don't get?
I think I didn't get the
So
problem.
if you have MU data, no noise, and you can integrate them properly, you can get the motion back. The problem now, to recover the motion of your camera from these measurements, right? You also need acceleration, angular acceleration. So to actually recover it, you have A, omega, and omega naught.
So,
Makes sense.
are we trying to recover the camera motion from the IMU data right now? Or are we trying to recover the
Yeah.
camera, I'm sorry.
We are trying to recover the camera motion from the from the MU measurements.
Okay.
But just put it like this, you can see the relationship between them has something to do with angular acceleration, right? So if you don't have that measure, no way you can mathematically reconstruct the motion. Even if you have perfect measurement and perfect integrator,
Right.
you still cannot recover it.
So you fix this by setting t to 0 and then we go.
Yeah, so if you set this difference to 0, meaning the two frames are just coinciding, then you can solve this problem. So Win is right. Right?
What is small t again? This transformation.
Yeah, translation between the camera and MU.
Yeah, T is this, this is from RU to, so this T is this vector technically. I'm talking about this vector. Is it?
Yeah.
Somehow, it's just this translation. I'm simplifying because we technically also have to talk about the rotation between the two frames. But let's just assume that the orientation of the two frames are the same. So mathematically, you still need angular acceleration to recover the motion of the camera from the MU measurement if you separate them. So to make it easy, just assume the body frame here, and then we worry about the motion of the MU, and then we can do the extrinsic transformation to get the motion of the camera if we need to. Okay, so be like in,
Even for IMU, it's word frame, but body frame, the t it should be not equal to 0, right?
sorry?
Even for IMU, it's body frame, like the one orange. It should not be t equal to 0 if the camera and IMU is not in same position, right? Why t is equal to
I
0?
think
If we set this to 0, if we set it to
Oh,
0,
So it's about how do you define your body frame?
Yeah, that's my question. Even the IMU, it's our body frame, but not the camera. The t is not 0.
No, but the T gives the transformation between the body frame and the IMU. So by selecting
I
the
see.
IMU as the
Oh.
body frame, T is by definition
but
0.
Oh, I think I can understand now. Because the t it's just joining the camera to IMU, so I think that t is the camera to IMU transformation matrix.
The way he was talking about it, it was like camera to IMU, but I think at the end of the day what
Yeah,
we just need to do is estimate the motion of the body frame.
yeah.
Mm.
That's
So
it.
if you have the IMU measurement, you have this. You do integration perfectly. You can get the position and orientation of the body frame at the IMU, right? And if you want to convert to IMU, sorry, camera, you just transform this from the from the body frame to the camera. You can, because this is a constant, you can do it. So you can get the
Mm-hmm.
R of the camera and the P of the camera. You can do this transformation. This is constant.
What so
Couldn't you estimate?
Yeah. What's the question?
I'm sorry, I need to formulate it.
But if you formulate your question.
But so here, okay, so if you assume that what you did there was what I think I thought in the beginning, that if you can relate, if you do the modeling of the motion in the IMU body frame, and then you have this transformation that is known, it's a really body
Yeah, we can
transformation.
transform to the position.
Then you can get
I can get a trajectory of the camera for example.
yeah.
If I have perfect integrator, I have perfect measurement.
Yeah.
Measurement.
Of course, not the drift.
I can get the motion of the MU and just do a transform to get the camera.
Yeah.
But if I put the motion of the body frame at the camera, right?
Okay, so that was the problem that you had here. If you put the motion in the camera body frame, or in the camera frame, then you end up with this problem, that you need to measure the angular acceleration.
Yeah.
Okay.
That was the same question. So we are contrasting whether or not to put the body frame in the IMU or in the camera or
Yes.
something else. Was that the problem?
That's the problem.
Okay. Thank you.
If you put the body frame in the MU,
Uh-huh.
in principle, you can do integration, get the trajectory of the MU, and apply the extrinsic transformation to get the trajectory of the camera, right? But if you put the body frame in the camera, you can integrate the trajectory of the MU, but you still cannot recover the trajectory of the ball of the camera because of this, just because of this angular thing.
Thank you. Get it.
So be like in, he knows. Okay. It's very interesting. I mean, the MU is when you start doing the derivative, all sorts of problems comes up. Okay.
If there is another IMU on the camera, then this
Oh, yeah.
will be a problem.
The question now, you can actually force it.
Yeah.
You can force the. You can, for example, you can use BS spline,
Yeah.
continuous time optimization to impose. That's omega is a polynomial. Then you can take the derivative of it. But it's a little bit advanced, so, but you know, right? You will do it. There are people who do
I mean,
it.
it makes sense when you say it, but
Okay, so I buy an IMU, I put it in Sweden. The Z is going down, right? This X, this is Y, this is Z going down. What are you going to read? If the IMU is at rest, what are you going to get?
Gravity?
Huh?
Just the gravity.
Okay, plus or minus? That's the big important question. So we have the IMU, we have the data. Have you got all downloads in your data set?
I mean, positive, yeah.
The
force is
set
down.
is pointing downwards, and yes.
Yeah, the z-axis.
So let's see
is pointing
the data set we got.
Yeah, his data set, huh? The first time I ran, oh, the ground is in the sky.
So we have a data set here. And so you say positive, who says negative?
I mean, I want to say negative now, but
Let's just make a vote, negative. Negative, no? Positive? Ah, okay. Rostopic echo.
this last time I checked, I'm not floating out.
Okay, so fly this back. It's negative.
Oops.
Is it negative or positive?
I cannot see anything. Oh.
Oh,
Negative. Minus 9.5. There's some bias there.
In the measurement model, you do plus g, so it has to be.
Doesn't matter. I can put the g is a vector, so I can put a minus of positive or negative constant into the z part of that vector.
But if you don't do it, then it's negative. That's
No. What I mean, mathematically, just use a plus for easy of understanding. But in engineering, you can put minus or plus 9.98 into that vector, no problem. But you want to look at that vector in a. So it's negative. Why is it negative?
Arguably, it's posed like this. Then.
No. My MU is like the MU I cropped into the image was the MU.
Is it compensating for gravity?
There's no compensating. It's just the physics. It's just physics.
Because its MU is like putting like this, and it's not like this one, but this one. It's MU putting.
Well, give me sometime like that. This is my
Yeah.
MU.
Yeah.
the way it's measured.
The Z is going downwards to the ground.
Yeah.
So it's physics. The reason why it's negative is physics.
That's about
So nobody had touched the MU before. This is actually quite like half of the day I was sitting there. Did I do something wrong with the driver? So are you?
No, I still don't understand why.
Yeah.
Because I thought you
I guess
defined the coordinate system with the z-axis positive downwards.
Yes.
So are you
yes.
measuring gravity or are you measuring the force opposing gravity because it's at rest?
So that's my question was
Uh-huh.
very straightforward, right? You get it and you hook it up and then you get a number. What is it? Of course 9.8 something we are taught like that in school. Question is positive or negative. If you have to set up the Z going to the ground. So
So you mean
naturally
if
you
you dropped
think
it from an airplane, it would be 0 actually.
yeah. So naturally we think that because the Z
Oh, yeah.
axis goes down, so it's aligned with the gravity, so it should be positive, right? But it's not. The reason is because next slide. I paused the slide like weeks ago. Nobody actually looked into this.
I like to be revealed in the...
So it's like Elon Musk, he
Beautiful.
shoots his rocket into the
Is that a
space,
car?
and he put a spring mass system onto the rocket, right? If you use the hooks, if you put your Z axis, if you attach your Z axis into this rocket, for example, I put the Z downwards, right? Then obviously because of the fictitious force, right? Because it's accelerating, so because of the fictitious force, the displacement of the mass in this frame is going to be the opposite of the Z, right? This thing, okay? So an engineer, he probably fired now, but designs the IMU is going to use this simple rule, right? You just measure the displacement, get the magnitude to be the acceleration magnitude, and then inverse the sign, right? You can actually rethink that if you put the Z upwards, it's also the same, because the displacement is always in the opposite direction of your frame of reference, right? If I put the Z here, well, basically when you go up, the spring mass system, I mean this mass is going down because of in this frame because of the fictitious force, right? So it's always the opposite of your chosen Z, okay? So this is the engineer how he designed the IMU. So if you put it at rest, gravity pulls it down. So it's similar to the rocket accelerating upwards, right? So so actually the IMU measures the opposite of the gravity. What the IMU feels is the opposite of the gravity. Okay? So negative. Are we like, can we sleep comfortably now?
I never do it.
Yeah, because you never will win. Yeah, this one is like how they put, how they design IMU. There's a mask here and there's some displace, there's some capacitor,
Mhm.
and they're going to measure the distance displacement by the capacitor, by the capacitance. Okay, we go to the technical parts. This is like, so I started having something to do with MU from very early on, but like, I think I started reading this paper. It's in 2016. And it has a word pre-integration. This one refers to this paper in 2011. So this pre-integration thing is actually quite a conventional method. Some colleagues from China told me they already studied this in aerospace 20 years ago. But somehow robotics people still like struggle to understand it. That's why you see some people still write a paper here, I write a paper here. Because most of these are on rotation matrix, and then when you do calculation on the Wattonian, you still have to learn a few tricks. So I wrote this one, and then I kind of put in some kind of tutorial in. So, but these two are similar, same. I should put the pin there. Same, but different. So this propagation means you start from something, you try to find the trajectory forward in time. The integration doesn't have anything to do with that kind of concepts. It's supposed to be an observation. So we don't have time to talk about details, so like let's just go through like my experience. Like, okay, I look up and they told me this equation to tell me this is propagation. So what do you learn from this one? So we have interval, right? We have some measurements, right? Some measurements, and then we do propagation. What do you, at least, you don't need to know the details. What is this trying to do?
Extrapolate.
It's Newtonian mechanics.
Huh?
It's more or less like Newtonian mechanics.
Yeah. So basically, this is just first order hold, right? So if you have the orientation at one time, and then you have the angular velocity at that time interval, you multiply it with the time. You assume that you are doing a constant rotation in that small cut interval. You're basically incrementing your orientation, right? So this is easy. And then velocity is basically velocity. The velocity of the next interval is basically the velocity in this interval with the constant acceleration multiple by time is basically the velocity change. So you add in the velocity. Then you use the velocity to update the position. So intuitively it's simple, right? You're basically just trying to dead reckoning your position, your states until the end of this interval. Right? So that's propagation. But you need to know the starting position, the starting states. You need to know your initial position, orientation, and velocity. This is why this line is important. You need to know this.
What is the relationship between n plus 1 and k plus 2?
N plus 1. So the last sample, the RMU measurements n, right? So the n equal to tk when n equal to 0. So the first RMU sample is the beginning of the interval. The m is tk plus 1. Right? So basically you have this interval tk plus 1, and then you're going to have RMU samples here. So this is the this is different index. They are just different indexes. So this interval you have different samples. So the idea here is just to do that reckoning of your states using RMU sample. Well, that's enough for us to move on. So then reintegration. The calculation is almost the same, right? It's just that now we start from 0. So there's no assumption on the initial state. Right? So that's why if you put them side by side, you see the first part is basically the same. The orientation part is the same. Uh-huh. The second line is almost the same. It's just that this side has G, this side doesn't have G. This side has G, this side doesn't have G. And the most important is this line. So this propagation needs your initial state to propagate forward. You don't know where you are, where you're going to propagate anyway. But this one, you just have a function to pump the data in, it's going to give you a measurement now. So
pre-integration was the initiation.
Hmm?
Was pre-integration the initiation?
So let's just say the last 3 slides, I'm just trying to tell you my experience. Because when I studied this one, I didn't actually know the details. I just look into the formulation and see formulation of propagation, formulation of integration. And so now first we need to know what are the difference between these two formulations. So for the propagation, you need the initial state. For the integration, you don't need the initial state. Right? So what are the differences? The differences
You
in
can
the
parallelize somehow, because I see that these are like two functions, and in that other function you don't have this initial state as an argument, so maybe that is being computed somewhere in parallel.
You can compute whatever at the end of the day. You have some numbers to work on. Yeah? It's not about how efficient you compute things. It's about you compute this and you compute this, but this one is used for one thing, this one is used for another thing.
I would guess the right side you use to make a residual.
Yeah, we will go to that slide. So first if we go to this slide, we just realize, okay, this one needs the initial state, the other one doesn't need the initial state. Right? So that's just the takeaway for now. And the implication and intention we're going to discuss next. But that's all. To make it easier, you can say this one is the velocity, right?
Mm-hmm.
So it's meter on the second.
Mm-hmm.
What is this one?
Angular?
This one is
Which one?
acceleration. This one
Yeah.
is time. So meter square. A meter on second square and second. So it's also meter on
Meter.
second. That's why in the literature they call this a pseudo or something like relative velocity, pre-integrated velocity. They call this the integrated position. Right? So
Should I ask a question about when we need the propagation and when we need the integration?
so this is also this thing. So we need propagation to do prediction, to do the motion compensation.
Mm-hmm.
Pre-integration we use it to couple the two consecutive states in the cost function.
There's no
Oh, I see.
G there.
There's no G there. That's why we can do that. We can.
It's
do
more generalized.
No, it's not generalized. It's so.
Just to be clear, the alpha hat or whatever,
Oh yeah. Also this
they're
thing.
very different, right?
Yes. Good eye.
So the alpha on the left side is acceleration measured, right?
The alpha on the left side is alpha. This one.
So A. Okay, it says A.
Acceleration. This one is also acceleration. There's also difference here.
Is it?
I mean, numerically they're the same. This is your bias estimate. This one is your bias guess.
No, I mean, for example, it says alpha n plus 1. And then it multiplies. It's on the. Here is where I wrote. So this, you said is position, right?
Pre-integrated position. So it's not position. It's supposed to be something else.
Okay.
Okay, so just to see the difference. Initial state, no initial state, motion compensation, this one for cost function. Okay, so now we're going to go, so now you're going up, like from the engineering point of view, you're trying to struggle how to understand it, but at least you just get a few of them in your pocket. Now we go top down, means you go read the first paper in that list I mentioned. This one. So no more slides. Let's say
You can insert a black PowerPoint.
Yeah, black or white.
Yeah, you can just insert. No need for. Yeah.
Can I insert another?
Yeah, and
one
present.
bond to Gryffindor.
And just present. No need to get
Yeah.
to black. Just a whiteboard.
White
It's
is
fine.
Okay.
Yeah.
So
Click the present. Maybe the button is not correct.
that are you confused enough now?
What were we doing?
That's why I say that view is always like
Just press presentation. wasn't
Yeah,
it?
yeah, press presentation.
On the,
That's what's like. But it's
there's a button.
That's he cannot. Yeah. Press this way.
Very
Yeah.
Right.
Right.
great.
So now take a deep breath, right? We are confused enough already. Let's take a deep breath and then let's see. Okay, what is one from the fundamental? What do we know? Let's just say you have perfect and you know noise, no whatever, so we don't have to worry about this. Let's just understand what it is. So you have. You want me to use Q or you want me to use R?
R.
Rotation.
Thanks.
So rotation at time t is basically
In the world.
in the world, correct. So dot is R omega, right? So this is in the derivative form. So you have something like this is sometimes something like integration of R omega. Let's just have say we have an integration on the manifold like this. Right? It's an integration.
It's like the
It should be a manifold.
Is it the T?
Yeah. Yeah. It's dt.
So like
Yeah.
tau.
Oh, tau. Okay, d tau.
A small piece of tea.
Oh, okay.
So this is the rotation. And this is like in the okay. So the purpose of the cost function is to couple the states, but now because we need to know the initial state, it's become a problem. So we want to make something like okay. So this one I can do this in R proximity pk. Is it okay?
Mm-hmm.
Sorry, no. Right. This one is constant. You multiply into this one. You just don't get this one back. And then bring this one to this side, so we have something like R, P, omega R, pk, and this one equal to that integration of the omega T. Right? So this one is actually, if you write it in a Patonian form, it's our gamma.
where did
No. This is not our gamma, but this one is our gamma because we are calculating on the data.
What is gamma?
Sorry, gamma.
In the interpretation, you have gamma, beta, alpha. Remember?
You can go back the slide.
This one. So you have the integration. We are integrating.
Why did the R come out?
Yeah, where did R go in there?
This one up.
No,
No,
the
it's
other.
The one inside the.
Inside the integral, there's a tr tau.
Down to T.
K.
So it becomes T.
So what I'm just trying to show you that is this gamma is a function of r tk and r tk plus 1. Right? So this is observation model, right? Because we do some mathematical manipulation and realize, okay, if we just integrate our angular velocity directly, we're going to get this observation model, right? So you don't need the initial state. In this integration you don't need the initial state, because if tau is tk, it's identity, right? So the integration starts from the identity orientation, right? So to recap, you pre-integrate the angular velocity. You can get in the perfect set, and if you have perfect measurement, you can get a relative orientation in that interval. So this is the purpose of constructing that gamma update rule. You want to find an observation model of a relative orientation. Okay. The four noble truths. The first thing is the model. So the thing that they're doing here is actually just trying to get to that observation model. Okay, so how about beta? You want? So clear, right? Basically, we have gamma. If you don't have any noise or bias, basically you just have gamma equal to gamma is an observation function on the relative orientation. Isn't it? Right? The first thing in the fourth step. So beta. So let's just say we have v t is v t k plus acceleration in the world frame. Right? This acceleration in the body frame multiplied with the orientation, you get the world frame. Integrate delta tau. dk dt, right? Then because this is the work frame, right? So what we try to do is we just try to do the same thing. Like we just now dt k plus r work frame times dk dk tau. Right? Okay. So this is beta. This everything in this integration is beta. Right? You throw everything back to this side. What you have is vt minus vt k minus. Oh, sorry. Sorry. Of course, how come you didn't mention
Oh.
the tau? Right? And then so dk plus minus g delta t. This is the sample time value, the delta sample. This thing. Okay. So plus g delta t equal to, and everything is r plus is equal to that integration of r right? So this one is our beta.
I don't understand why there are two R's there. on the right hand side.
You this one is a constant, right? You multiply this one into this one, you're going to get the rotation in the one frame. Is it clear?
Mm-hmm.
You factor it into two pieces.
So what do we have here? So what we have here is beta is an observation function of R K V K V D plus 1. So this is the whole motivation. They want to construct the observation model. This is another observation model. So now you already can guess what they do with the alpha, right?
What is the difference between VT and VK? It's
These are just like putting the T here.
So you can remove, yeah.
So I can put the TK, put the N and TK here. So I just
Confusing.
Uh-huh.
Right.
So now we can guess that H is already something like RK, BK plus 1, BK. Yeah. We kind of guess. Which is because if you just do the same thing here, so did you write out the true form of this one? I erase it already. So BT is BTK plus what BTK integrate over the we need to do this integration is BTK plus integration of A This is the alpha, and then you also do the same trick where you just like the B dk plus B k dk plus B plus R plus times integration A plus delta P square over 2G then plus R
Do minus the G term.
Yeah, minus. Yeah. And pull all of these to this side. So we have the integration here, which is alpha. Right? So alpha is basically bk dk plus 1 minus b dk minus b dk over 2 plus over 2 squared g. And then everything is inverse. Yep. So this is our observation model here. Do I miss anything? Yep. So the purpose of the integration is basically to find you the observation model of the state. That's all. To consider it.
Oh, so this one is the height. Z.
No, not the height. It's the function. It's a function.
Oh, I mean the PT. Because your acceleration is gravity, so it should be height.
Can you point?
Gravity is a vector here.
Oh yeah, gravity is a vector here. It's a vector. It's a
yeah.
0 minus.
Oh, vector here.
It's a
Okay.
pretty vector.
Thanks. Oh, because you write that G, so I think it's
So
Like a bulb G.
at the end of the day,
Yeah.
you know what our forefathers were trying to do, right? They're trying to construct the observation model of these states without having to know. For example, if you do propagation, you're going to need to worry about the initial state, but now you don't. You just directly integrate, and you have a nice observation model.
So this gives you an observation model between time tk and tk plus 1.
Yeah. Whatever state you define this time, whatever state you define this time, you don't need to worry about them. You can have the relative relationship between them from directly integrating the IMU measurements.
And what's must be a very stupid question. What's the observation model if we do IMU propagation?
IMU propagation you can't exactly you cannot do the. If you do propagation, this is the propagation. This is like the form of propagation, right? Then you have to start from decay and you propagate forward, right? But as I said, when you do propagation, you need to know the initial state, so you need number has to be known. But in this case, we don't know it, so we can throw it into our observation model. Is it clear? So there's no observation model. You really can't construct the observation model with the propagation calculation, because propagation and integration start from this same equation. The thing is, whatever they don't want to throw it to one side to construct the observation models to be estimated later. This propagation model, if you know this one, then you can propagate. But if you, because you don't know them, you throw them to one side, like this, and you can start doing the estimation. So in principle, technically, if you just do calculation, right? If you just integrate and then you know the initial state, you can actually use your integration numbers, alpha, beta, gamma, to calculate your end state. So to recap, the integration is to construct the observation model, because we don't know the initial states. So we can construct an observation model and all of the unknown are put into one side to be estimated. And then because we write it in the rotation matrix, so it's easier to understand. Okay, so there's another trick. So far we've ignored the bias, right? But life becomes ugly when you start worrying about all of those details. So let's just say we have the IMU data here. Let's just call this this whole data. The whole sequence we have is this data A, right? So what we've done so far is we get alpha, beta, gamma being the, so this is, let's just call this the pre-integration operation done on our data, right? And we get a nicely model of the RK plus 1, PK plus 1, BK plus 1, okay? So we've been able to do this, right? This is the pre-integration operation on our whole IMU sequence.
What is so in the curly bracket? It's a sequence. Okay.
Yeah, I'm denoting a set there. So what we have is we have a sequence of IMU data. We've done the integration. You get U alpha, beta, gamma, and it's the state. It's connected to the states through the observation function, right? The problem now is we have the bias, and we to do this integration you need a bias, and it's actually the bias is here. Let's just say I call it the bias here, and this is also a state that we don't know.
Isn't it constant for?
Yeah. So what they do? That's what they do. What they do is they assume they know some kind of close estimate, right? And so they calculate this alpha, beta, gamma based on that assumption. And they're going to modify their observation model by, so this is G, right? Plus delta G, delta B equal to B minus B constant equal to H. You get what I mean? So you get this one, and you get this one. So what they do is alpha, beta, gamma equal to G plus minus H plus, so is equal to G equal to, H minus delta G delta B. So this is the new observation model that has the states here plus the bias states. You see the technically, this, so they do all of the integration on the IMU data with a guess on the bias, and they say, okay, if the bias is actually changed, then they change a little bit, that you can approximate this whole function with this linear approximation. And so they throw this term onto this side, and this is our new observation with the bias. Yes. And then this is our observation. That's the genius idea of that TRO paper. Start from the guess, do this linear approximation, throw the linear approximation to the other side. You can recover the first noble truth, the observation model. And then the noise, which is overkill. You need to read it. I really like. I mean, you can understand the noise. So basically, if you have the noise, you're going to have a noise somewhere in your observation on this side, right? But generally, you can throw the noise back into this side and solve it. And the noise, the error, can be updated iteratively. Right? So when you do this function, the integration, you can use the same covariance propagation method to propagate the covariance noise. Okay. So you see, AMU is like a very hardcore sensor to handle.
I didn't understand what they do with this.
So when you get, do you get a point like what we do at this point?
Yeah.
Right? So you have the AMU measurements, you trying to integrate them to get you some numbers. These numbers are connected to the states by this relationship. For example, just now we mentioned V beta is R minus Vk plus 1 minus Vk Vg. So this is the H. This is the H function.
And here G is gravity.
Yeah, G is gravity.
Not in that.
No.
Yeah, not that one.
Here,
Yeah. No, there.
Yeah.
The G is gravity.
Not here.
Okay. So did I deliver this idea to you?
Maybe you can drive it home by just again repeating what the cost function for the IMU looks like. So you see H, which contains the state parameters you're trying to estimate, you have the measurement, and you're trying to optimize this to make the residual as small as possible.
Yeah. So but the idea is, whatever unknown, you throw it into the one function, and the other side is basically just everything you can observe. Right? Our computer camera you can observe here, and the state you don't know here, you have a model. So, and then the genius idea is basically because they don't know the bias, they have to start from somewhere with this trick, and then put this also aside.
Do they estimate the bias while the method is running, or?
Yeah.
Yeah.
It's optimizing the bias simultaneously as
Yeah.
states. The bias is part of the state.
The bias is a state.
So
Yeah.
this slide, I was just the whole time I was just trying to explain this slide.
Is there like research on
This thing, every on one side, all of your observable numbers on one side. And so this is the model. Noise and bias, we don't pay attention now for the sake of understanding it.
Is there like research on what would happen if you had a second order approximation of the bias? Like is it?
I haven't seen it. I think it's overkill.
Yeah, I'm just curious.
Yeah, so the residual is basically just now I said you already get a model, right? what do you do with the model? You ignore the noise, you plug in your estimates, and then you take the difference between your measurement and your model. You see, this is what I mentioned just now. This is the G on the bias with the B minus B. Yes, this is what I mentioned just now. Right? So the residual is like this. That's why GTSAM handle this for you, even though this annual integration doesn't have anything to do with graph optimization. And they handle it so, and they also assume something in that application. Yeah, any question? This. I'm using the residual calculation on the quaternion, so it's a little bit unfamiliar. But it's the same as like R minus R.
So the capital B describes the plane.
Capital B.
B sub omega. In the purple.
Purple.
Second.
Yeah, this one describes that this
So this
G,
is
the B. It's a Jacobian. So when you take the Jacobian of this residual, for example, and when you take Jacobian of this RB, R beta, you take the Jacobian on the bias, right? Yeah. What you get is, for example, if you take the bias omega, what you get is only this one, right? And the other terms thrown away, you can just keep this one. Is it hard? Yeah.
Yeah.
Pretty.
Yeah.
It's a lot of new information.
It's not new. It's because the paper, the first work.
For us.
It's new.
He's saying about the community.
That's why do you think I would be moral? Do you think it would be moral for me to do this kind of assignment on this thing? I stop at the propagation only. I could ask you to go design this.
I was going to ask, do you expect us to write this in something?
Which is overkill, right? So, but what I do is I understand it, okay, right? Then I copy the header. I copy the header that defines this angle factor, right? And I just define, okay, this factor, what is it coupled with? Position and time, position, velocity, orientation, and time decay, and decay in first one. Just those states, right? I just declare it in the header and then use it. But of course, when you dig inside, it's very, a lot of brain came into this one. Right? And they did this thing where at Binance, they did this trick. I don't know whether they did it earlier. Yeah. So the Jacobian and Jacobian is really hardcore because you have to do a lot of Lie algebra manipulation when you have to use your identity to shift the noise all the way back, because the noise is coupled in the middle. Because every time you, for example, every time you do this Rn plus 1 equal to Rn, and omega delta t with noise, right? What you do is you're going to have a chain. 1, 2, with the noise here, then with the noise here, then with the noise here, right? So the noise are in between all of the terms. So they have to use your identity to bring all of the noise to one side.
Yeah.
I'm like talking out of my ass with you. That's why I don't want to like introduce. It's going to take forever to finish it. Is it break already? Yeah.
What's on the next
So-
slide?
I'm also curious about what's on the next slide. Oh, okay.
Enjoy the ride, right? So is there any question?
I have a question, but it's not really related to
Elon Musk.
this.
Not related to Elon Musk?
No, not necessarily. No, because like when I was looking at the series library, and they actually do, they say they do automatic derivation, derivatives and stuff. So does that mean? So that means we don't need to compute the Jacobians and covariances on our own. Is that?
It's slow. For one, it's slow.
Uh-huh.
The second one is they use jet numerical tools to do that kind of thing. So if you have a complicated function, it can be very slow.
So is that why you write out your Jacobians
Yeah.
on your? Okay.
There is, however, for PyTorch, a Lie algebra
Auto
thing
into.
that you could just write and then take the derivatives.
Yeah.
So
Lie torch, it's called.
that with we are done with the sensors.